So for our last presentation for this session, we have someone that we all know from yesterday, Sam Ritchie, who yesterday told us the things that are theoretically possible. And today he's going to dazzle us with actually showing us how it works.
You're talking about how getting something to display on the screen behind me works?
Let's see how that works, yes. You have to plug in the...
Oh, yeah.
Is that what you expect?
Yeah, that's what I expect, kind of. Now let's do...
Did I miss a question?
Okay. Come back to here. All right. Worst case, I'll just use the mouse. Yeah, that's fine. Okay. Is this working? Can anyone hear me? Okay, where were we? Welcome to, I guess, the second half of this two-talk series. Yesterday, if you saw the talk was about this, well, about literate programming and how we communicate with code, but I showed some of this library, this SICMUtils. I don't think I explained the name. It's a pun on, it's not a good name to start with. It's a pun on SICMUtils, for you have SICM as the structure and interpretation of classical mechanics. If anyone has a better name for what this is, like that's the real goal of this talk. Come up with a nice name for what we're making here. Okay, so the agenda, we're going to talk about what's in the library. I'm going to give a fairly fast overview, but please stop me with questions as you go. I don't know who here is familiar with kind of the guts of a computer algebra system. I'm going to talk about some of the techniques that I used to implement this, many of which came from the original library, but some were very kind of nice additions that Clojure as a Lisp and its opinionated design pushed on me that I found to be very nice. We'll also talk about some I guess, issues or problems or just things that I'm a little uncertain of or that I'd love feedback on, and then I'll blast over to explain that notebook environment that we looked at before and show some demos of what the system can do. Once again, thanks to Gerald Sussman. He wrote the original thing. He also has a book out that I don't know if you've seen called Software Design for Flexibility. Clearly, having done this whole process, that book is just his lessons learned from the 30+ years of making this library. So many of the techniques that he writes about here honestly don't make that much sense if you just read the book. You might say, well, what would you use all this for? What you'd use it for is a big computer algebra system called SICMUtils. Okay. So the goals of the project, pretty much what we talked about yesterday. I want to be able to write and communicate software and mathematical ideas. I'm convinced that to do that well, you also need to be able to read something in the same environment that it was written in so that you can play. I guess the analogy would be the workshop. You go in the workshop, there's tools everywhere. You can go hurt yourself if you want. That's totally allowed. If there's a sort of crusty old machinist or wood expert in the shop, you can go ask for help. But pretty quickly, the goal is to let you be off on your own making things. The library is meant to embody that experience and be a thing you can read and absorb. Oh, and a key point about that is that there was a question yesterday about what's the difference from existing computer algebra systems. This is meant to be a collection of many small pieces that people can steal. So if you just want to do symbolic representations of S expressions and pass in symbols, that should be a thing you can swallow without this whole physics mess that we're going to talk about. If you want to go all the way up to Einstein's field equations, take the whole thing, but LaTeX rendering, all this stuff should be like fissionable off. And I expect almost no one will read kind of the full thing, but the pieces will be quite useful. And that would be success. As we'll see again in the demos, it works in many different environments. This is part of the goal of you should be able to read the stuff anywhere. Obviously, the REPL. Nextjournal, which I'll show you, is a JavaScript only. It's a web interface where all this stuff actually works. So you can write something in a sort of online notebook. You can get something animating and running and doing tech and send it to someone else, and they can edit it with no environment other than their browser. Org mode, these slides are, org mode's awesome. So yeah, obviously the stuff works in Emacs. Clojure is the JVM version of Clojure. Clojure script, for those who don't know, is the compiled to JavaScript version of the language. The whole library works in both. Zeugma is this sort of wild room-size fit animation environment that a colleague of mine has built. And the ODE routines from this can power that environment too. TechMax. Eventually, I want to get this stuff into Roam Research, one of these online note-taking environments. But yeah, OK, what's in it? It's a huge library. It's 27,000 lines of code. There's 25,000 lines of tests. A lot of that is generative testing. That's been really helpful. I made this. I exported a graph of the namespaces, and I thought this would be really elegant and just show the development of modern physics. It's like not very nice looking, but I still thought it was cute to include. Here's Quadrature Island. This is how you do numerical integration. So there's a lot of stuff in here. Going through the list, you start with numerics.
We have an interrupted question from online. Do you want to take questions or save
yeah,
them to
sure.
save it to the end?
Please.
So the question is, Sam, what software are you using for your browser-based presentations?
OK, for the browser-based ones, I'll show that off in the demo. But it's a software package from Nextjournal called Clerk. I'll go into more detail about how it works, but it's also a Clojure library that can basically watch source files as you develop them and render. And it's programmable from within Clojure itself. So it's kind of an extensible notebook system. So yeah, great question. You'll hear more in 10, 15 minutes. OK, so step one, to run in all these environments, these are the basics. We have a numeric tower. That's fine in Clojure. Lisp gives you kind of everything that you'd want. JavaScript does not. So step one was getting ratios and big nums and everything up to complex numbers working in parity in both environments. There's a lot of things that look like numbers, meaning you can sort of add them, subtract them, multiply. Dual numbers are a thing similar to complex numbers, but you use this for automatic differentiation. Quaternions, I don't have anything beyond that in the stack of octonions and Sidonians, but it's coming. Split complex numbers. The library is really a big, suite of generic extensible functions. I know this is pretty familiar to common Lispers, but it's not a normal thing in Clojure. So all the functions that I'll show in the next slide, pretty much everything can be extended either by class or in a totally open way, the sort of multi-method function-based dispatch. So the first example is, we're squaring the plus function. What does that mean? It means we're going to make a new function that has the same inputs as the original plus, but after you eventually give it something, it's going to go basically compose square onto the end. So this is nice. A lot of mathematical notation is things like x plus y squared minus this, but really those are meant to be functions of time. So this lets you write big mathy stuff that looks just as obfuscated as the normal, and then pass things in later. Bottom one is pass something concrete. The first one is we pass symbols, and all that dispatch happens at runtime. Here's examples of generics. This is just the big kind of grab bag that's in the library. There's more than these. Obviously, you can make your own generics. You can use the tooling in the library to gang on all the dispatch that we have, or you can go ahead and just use what Clojure gives you. You know, it's Lisp. Feel free to break out. Okay, so symbolic computation. You saw a touch of this before. You know, it's pretty easy to imagine what symbolic computation is going to result in Lisp because you just have S expressions in, S expressions out. But the simplifier is pretty sophisticated. It's able to go take massive expressions that might pop out over the course of a computation and do a good job of simplifying them down to the tightest representation it can. Okay, so you go from numbers, you go from symbols, you go up to compound data types, vectors, matrices. All this stuff is like hard, it turns out. Polynomials are just, making this library is the process of me discovering that there's more than meets the eye to everything you could ever imagine programming. Like the polynomial package was like a month of just researching how hard could a polynomial GCD be? Greatest common denominator of 2. Really hard and like a totally not done problem. But it's all here. We have power series. Quaternions are kind of a compound data type. A very powerful thing you can do is define literal types. The symbols we saw before are meant to be real numbers. You can also say, OK, I'll make a literal matrix. And what that can do is all the operations that are defined on matrices, they just build up an abstract expression tree. And later, I'll take that and compile it down to a concrete sort of matrix representation. Or some operations that maybe run on the GPU, maybe do a browser-based thing. So this facility for building simplifiers and declaring different types of literal things turns out to be very powerful. And it's, again, a thing we just get from Lisp. There's a team working on a quantum mechanics package that can go render bras and kets and do quantum simplification. And that's useful to that group just as I want to write this stuff in papers and not have to go fiddle with LaTeX. That's valuable beyond any of the simulation work. There's a pattern matching DSL for declaring a lot of those simplification rules. I implemented this based on techniques that Sussman had in the book, so that also is kind of literate programming package. I hope to read this, we're out of Clojure, we're in macro land. Basically, the first pattern says, if I'm dividing anything that's some prefix, could be empty, some suffix, and then an x times the square root of x, just go ahead and push the square root, or divide that square root out of the first x and just leave the numerator. Combinators, you can take rules. There's functions that will take something that looks like a rule and spit out another thing that looks like a rule. So anyway, this combinator idea is like all over the library. And that was very, very useful for writing the sort of 1,200 lines of simplification rules that are in there and condensing that down to something nice and readable. Here's a pattern combinator to do derivatives of literal functions. This says the choice function takes multiple rules, any number. It says try each one, return the first one that matches, and if nothing matches, kick out a failure. So it, of course, matches the rule interface. I won't show the alternative that was there before, the kind of non-pattern matching code, but the lesson here is like, if you want to go, try to make things easy to understand and read. Make DSLs, don't worry about it. And yeah, you end up with things that look fairly nice in this case. There's so much. We have renderers. Here's an infix renderer. This goes to the best ASCII it can, given some symbolic expression. The tech renderer kicks out a LaTeX string, which I think feeds off the end of the page here. Here's one before the whole JavaScript implementation. This just kicks out JavaScript source code in case in the pre-ClojureScript world you want to go just embed this in a web page. So there are many nice demos that people had done with just these things copy-pasted into websites. You can start, one I guess, message I want to get across about this is using Lisp and using these sort of generic programming techniques, I found that the library got easier to work on as it got bigger. One example was trying to make things fast for numerical simulation. We've got a function here, myFn at the top, just uses a bunch of operations. they're all generic. So I can implement a compiler for this by gen-simming x and y, passing in these auto-generated symbols. I get out my abstract syntax tree, simplify it, pull out common sub-expressions, rewrap it up in a function, and I call eval on this or ship it off to the browser. And it's just no problem. The simplifier is able to kind of help me there. This is, again, where those literal matrices with their own set of simplification rules and their own backend that you compile to is an obvious kind of other target. So the more kind of connections between things, the easier it was to just get things like this for free. I'll blaze through the next couple. There's just so much. I just put these in the slides in case you're interested. But there's a ton of numerical methods code. We can do, you can minimize things. You can go interpolate polynomials. It all makes sense, like in the narrative story of physics, but it's just this massive grab bag. We can do automatic differentiation. Oh my gosh, there's so much. Animations. This is kind of the latest thing that you saw a little bit of, this idea that what if I wanted to break out of symbols and have a visual REPL available? Well, many of these mathematical concepts have natural visual ways to look at them. So, of course, there should be a module that provides a whole grab bag of, I've got a polynomial, can I look at it? Can I go ahead and see its derivative and look at that too? Yeah, also very, very helpful. OK. So I mentioned a few of these, but I just want to call out a few of the programming techniques that appeared during the development of this library. One, as I'm not a Common Lisp programmer myself, but as I understand, there's nothing new about this idea of just extensible generic functions. It's not common everywhere, so I don't need to pitch that very hard. The second one is Clojure is pretty opinionated. It really likes immutable data. There's a very small number of core data structures that you're sort of pushed to use. I found that to be very helpful to accept those opinions. The combinator idea is very nice. And then this pattern matching DSL was just another example of being able to break out of the core language you're in, like Clojure in this case, and write sort of other mini languages is also just a wonderful technique you get for free in a Lispy system. OK, so the generic dispatch works here on single functions, single argument functions by type. That's pretty fast. We also do this thing. I don't know the name for this, but there's a hierarchy of keywords you can install in Clojure where I can go ahead and ask some type its kind, an instance its kind, and that keyword, in this case, a complex number is this namespace complex keyword. That will go feed into a different dispatch system. The reason that's nice is you can do things like, these are the multiplication method installations for matrices. I can say, if I want to multiply a scalar by a matrix on either side, go for, here are the two methods. But then scalar itself is something that you can come in with a different type and extend scalar to your own kind. And then other types, other sort of instances will be able to play. So you have guardrails put up. Usually a matrix will say, I don't know how to multiply my special JS number type you implemented by the elements inside this matrix. You can sort of open the door and allow that. I don't know if that's like a great design idea. I spent a lot of years in the Scala world. I was doing like strongly typed stuff. This feels a little janky. I want type classes everywhere, really. But honestly, it works well. And it's been a lot easier, I think, for people to swallow. So that's another kind of, I think this is a good design decision, but I don't know. Sticking with Clojure has been nice. I'll go to the next slide to show this. Clojure has this small number of core data structures it likes to push you toward. There's vectors, there's associative maps, which are the curly braces, there's sets, and then lists, as we all know, and then keywords and symbols. But there are many, many new types in this library, like quaternions, and we have these different sort of non-vector structures that can combine in different ways and be applied as functions. But they all implement all the core interfaces, so you still get to take advantage of things like Clojure's destructuring binds. And if you want, you can break out into kind of normal Clojure land. that has been so nice for interoperating with other projects in this ecosystem. There are so many closure libraries where people go, I think I could use that, or let's get the linter going, or let's get, the notebook example will be a great example of this. It's just so wonderful to be able to say, you know what, I can drop out to a kind of core closure data structure and serialize to you in a nice, rigorous way without worrying too much. So yeah, that's good. Freedom is good, but constraints breed creativity. You know, don't go too wild. Yeah, combinators, we'll just go past. I'm trying to rush to get to these demos I have. So stop me if you want to see more of this. This is just a short kind of pattern matching example of how to build up something pretty complex pretty fast. Here's a rule that will go ahead and do, you give it a sequence of symbol operations, and it says, okay, well, if I have any of those operations with just one argument, just strip the whole thing off. Rule set will actually make this thing descend down into a syntax tree. Constant elimination is same thing. If I have like a, you know, plus and anywhere inside there's a 0, just filter that out. Constant promotion is the opposite. If I multiply anything by 0, like anywhere in there, just kill the entire expression and replace it. And so you can make a simplifier that's pretty sophisticated by just plugging together these out-of-the-box like Legos that describe different mathematical properties. So it's actually pretty easy to make something like a matrix simplifier just given a few algebraic sort of constraints. And then the example of that, you know, simplify that ran in the slide is go ahead and take something with a bunch of goofy stuff, like we're adding zeros, you know, to 12. All that can get stripped away, and that all runs nice and quick. And here's the simplifier for differential operators that's in the library. It's like plus and times are associative. Anytime you see things multiplied next to each other, don't switch them. It's not commutative, but you can make exponents. And then go ahead and kill unary pluses and times. That's the only rules. I showed this example before, but this technique's like really powerful, this multi-stage programming. That's the name for this idea of just being able to produce, like at runtime, an abstract syntax tree and then go kick that out to some concrete physical representation. After the talks yesterday, I'd love to get like, you know, a SIMD, get the stuff working with SIMD. It's a little kind of goofy because we're not in macro time here. We're still sort of calling a val, but that's the flexibility you have is at least nice to explore and play with. Okay, let's see. The Clojure community's been pretty amazing here. As I mentioned before, Colin Smith started this library. Clerk is the notebook system we'll talk about. This is meant to be like a feature that I'm showing, not a thank you, because there's just so many lovely projects here which were very, very easy to work with because of this. Like, Clojure's very friendly, all the core data types, people can talk. So yeah, keep bottlenecks in your project so you can talk to other people doing good work. Yeah, I'm not sure what to highlight about what's been hard. One hard thing was called out yesterday is there's no types on all this stuff. So you haven't really broken the problem of you've got to know like the culture of what is even in this stuff. Like what do I do with polynomials? What does Lagrangian mechanics mean? I think that's an open problem. Clojure has a nice optional typing system, and I think there's many kind of levels of type information you might want. So it's been hard to get people to work on this without that. That's going to be a thing I need to add. Another thing is, with a project like this, you have a lot of information available that you can use to go walk the project itself that is not exposed now. Like, which types implement plus? You know, what can talk to what? What are the different implementations installed for this other thing? And so if you want to go look at a concrete example, you can go back to things like the derivative operator and so on. But you can't ask the derivative operator where it's used. You can't sort of see this graph of associative connections. That project will be interesting, and that's one almost of pointing like a viewer at the library itself and saying, what can the code tell us about the way that all these ideas are connected? And that's just the context demo I have here, too, or bullet I have here, too. OK. So final kind of demo and then if you see anything interesting, please ask questions as I go. I'm going to pull up this. Where's this? Okay.
Sam,
Yeah.
there's a question here from the people online. They ask if you can share the code for the slides.
Oh yeah, totally. Yes, the code for the slides is on GitHub, and I'll have on the last slide. I'll put the link up to that, or it is up, so you'll see it. Yeah, the code for the slides will all be up. Okay, so can everyone see my Emacs and then the browser window next to it? Okay, I'll make it bigger. Don't worry. Just sit down. Okay, so I want to say a little more about what we're looking at here. On the left, is that bigger? Okay. Is everyone awake? Okay, we've got Emacs on the left. This is a closure source file. On the right, we've got in the web browser, we've got a page here that's a kind of notebook-looking rendering of what's on the left. And what's exciting about this, it's an open source project. It's called Clerk. It's it's an opinionated take on notebooks. And the opinion is that notebooks are wonderful. It's great to have a visual REPL. Nobody really wants to leave their editor that they've spent decades learning and go to these not perfect yet IDEs that live in the browser. It's just kind of off the table for, probably everybody in this room. But what do? Do we toss out the web? So the take that this library has is you can sort of write things down, just code, and then ask the system to go ahead and, closing my laptop always goofs this thing. Let's see if I can get this to work. You can ask it to go re-render the Yeah, there we go. So it's fairly quick at going ahead and just sort of live updating whenever you ask it to. You can have it watch the file and do this on save. Clerk's actually is quite bright about using the Clojure compiler to go build a dependency graph of all the vars that live in the namespace. So if you change, you'll get the experience. What it'll look like is that it's rerun everything from top to bottom every single time, but it'll do kind of minimal work possible. You're not left with this inconsistent notebook that no one else can run. So just a couple examples. Here we have on the left, I'll go through it on the right. We've got some expressions. Oh, look at that. S expression leads to S expression. Clerk has many viewers built into it that can take your output and interpret them, in this case, as math. So here we have sine squared plus cosine squared rendered as tech. The system, this is kind of the best thing. It's extensible from inside your non-browser Lisp. So read this more closely if you're interested on the Git repo. But basically, you can say, I like this tech. That's nice. I'd also like to see the associated closure with it, just so I can toggle back and forth. Maybe that's something I want to do. So we implement a function here that just makes a pretty printed version of a form. We do another one here that gets a closure dictionary with 4 entries. I want simplified LaTeX. I want the simplified form, and then the non-simplified copies of those two. And if we call that function with our initial input, you see that we've got this nice, kind of visual REPL representation of the dictionary, which has, tech, but the value's rendered as LaTeX. And here the value of simplified tech is, well, it's a tech 1, if you can tell. And then you can do more. You can make functions that will ship source code over to the browser that the browser will then execute for you and kind of mold this environment as you go. So here we've got this kind of gnarly, big, basically HTML blob that is coded in Clojure. So keywords get mapped to, in this case, classes and things on the HTML. But just pretend that I know this stuff cold and I could live code this. We've got something basically that will take that data structure, spit out a new viewer with a render function, and oh, voila, look at that. I can say, show me the expression I had before, use this new viewer instead, and we get this, I don't know if this is great UI, but toggleable thing, this thing with little menus where I can flip back and forth. And if I then, let's see, go, I don't know, let's cube the tangent of y. That's a nice, OK, that can't be simplified as much. So this thing will just live update, and you can see that, yeah, the simplification is a little tougher on that one. I can also go ahead and install this for all the forms in the namespace. So I can clerk show that next line that said set viewers. And then if I scroll to the top, everything will have been redone with that new viewer that I made.
Before moving too far, I had a question about the problem of the types.
Yeah.
So you're saying sine square plus cosine square is 1. So you're assuming that x and y are numbers.
Yeah, in this case,
If they're matrices, it's the identity matrix, for example.
Yeah, in this case, if you just pass in a symbol, if you say symbol x, that's assumed, that's, I guess, coerced to a literal complex number. If I wanted to...
So why is it assuming numbers instead of any other, I don't know, what the most
just
general
because...
case, monoid or ring or...
Yeah, just because that's the most kind of natural thing you do, there's a constructor to make them explicitly, like a literal number constructor. You could, I guess, I could write a function that switches the default to be literal matrix or something. But yeah, just the pragmatic, like, what do you think you're going to get when you say, plus xy, and then you compile it to a function. So that's the out-of-the-box, like, batteries included decision. But no reason other than if you were working in a machine learning lab or something, you'd probably switch it. So that you had to explicitly call out, or make a naming convention or something. It does matter, though, as you're saying, because which simplifications do you apply? These things are all, they kind of infect anything they're combined with. So if you start with the right types at the bottom, you'll get, you'll stay as you go. That's an example of something missing. It's like, actually, the print representation should probably tell you, what this tree is. Yeah, I don't know. I think this is so cool, like being able to live change the stuff from inside the browser. So really, last week, I went pretty bonkers on this. Well, it took me like 6 months, but I adopted this project called MathBox. It's this, it was running the demos yesterday. It's this beautiful JavaScript library that this sort of mad genius created. It runs only in JavaScript. He's got all these amazing presentations. So I took it, I got it working in sort of modern JavaScript. I then got it working with ClojureScript. And just in the last week or two, I was able to use it to make, coded in the browser, this like function viewer. So I can take a Clojure function. Yeah, let me just show this. So I've got here on the left just a Clojure function. I can insert, here it is. It's my function. It's great. I can go ahead and call it locally. So I can, let's give it 2. Great. And this output will live update. So I can do all the things I did in the previous slide. This is like totally generic. But I can also pass it to the function viewer. And because it's a function of time, it will call the compiler that we showed before, but just produce source, not do any evaling. Send that over the wire to the browser environment, which has the entire library available as well. On that side, it will eval into a proper function, and then pass that into MathBox, which is every 60th of a second calling and rendering this thing using the GPU on the machine. So below it, I've got, what do I have here? I've got a similar thing where, let me zoom in on this. Yeah, we've got, here's the function that's being rendered, and then below it, I've got the tech version of the function. So if I go change the function again, like my function here, let's just take t out and change this to, I don't know, tangent. If I clerk show, then the whole thing will re-render. And I've got this. Let's reload to get it kind of started again at the right spot. Yeah, now I've got this function here. It's not updating, but also the tech has updated below too. So if I put time back in, if I, let's say times time, 0.01, just or 0.1, just to slow it down. I do clerk show, and suddenly, okay, this thing's live animating again. But I've also got the viewer that I wrote on the other page, which now is just a closure value. It's available to anybody else. I could publish that as a library or send it over to someone in the gist, and then they would have the same ability to view and interact with code the way I have now. There's also facilities to go publish like a static piece of HTML that anyone can just interact with without having to go boot up an entire environment. Any questions on that? Oh, do you mean the microphone? I can just repeat it too.
So I want to ask, so how hard is to maximize Emacs?
Yeah.
I'm using a new plot to get the plot that doesn't move that much.
Yeah.
That's really interesting. How hard would be to integrate into another, say, system package?
You mean I'll repeat, but just clarify. So to integrate this stuff into a different package, or to integrate that sort of new plotting here?
So integrate this kind of plotting into another software, to say that, another language.
Yeah, it wouldn't. So the question is, how hard would it be to take all this stuff and move it into a different system that isn't, eating the entire closure cake? The way I've built it, it wouldn't be difficult at all. MathBox is its own library. There's a project we're working on now that it wraps it in React components. So one, you could just use it from JavaScript the way it's meant to be, or two, we could write a small kind of glue wrapper that knows how to just take serialized S expressions representing functions, and you could tweak that a bit to say, well, this is the output from Scheme, this is the output from Common Lisp, and just sort of slot things into the right spot in the function viewer. Two other things I want to show, and then questions, or I'll shut this down. One nice thing about this hybrid approach, where you're on your machine, you're on, in this case, the JVM, but you've also got the browser, is you can, if you put state in Clojure's atom, in kind of an atomic reference, you can make components that live in the, okay, so here's a cube. This is a cube that just has a bunch of points in it, rendered by MathBox. Here's a different version of the cube which has these sliders. And it's ugly, so I won't show it. But the sliders are defined the same way the other example was. We've got HTML that I wrote in Clojure as a quoted form. But they are able to, as I move, feed their information back to the server, which will actually change the server-side atom, which will then trigger a re-render back up of the page and modify the animation. So if we look at the bottom here, I've got basically an atom with entries that define, okay, I want width, height, and depth of this thing that I can interact with. I've got size and opacity. And then this is, let's see the contents of that atomic reference. If you can see below, it might be a little faint, but if you look down here, as I change the slider, those values are changing. And then if I go to the REPL over here, let's see, at box state. Yeah, as I go to the REPL here, I can make this go up and then ask again. And I don't know if it's obvious, but the opacity is now 0.55. And it was, before all these recomputes, it was a much smaller value. So immutable data is great. I can then take this. I can say, wow, I really like the state that I got to here. I can paste this in as my new initial value, commit that. And this sort of, well, the visual REPL is nice, an interactive visual REPL where I can get to different initial conditions and then go back to source code. This is kind of a new way of working for me that I'm excited to adopt in the context of a lot of these sort of physicsy animations. A final one, I guess, to show is we've got the pendulum example. Just because of charting, I want to show. This one takes a second to run. Let's see. OK, here we go. So this is a big one I'm not going to go through in its entirety. But basically, we've got here a, once this loads up again, it's a simulation of a double pendulum doing its thing. A double pendulum is an interesting system because You can start it, there's certain initial positions where the pendulum will be very smooth, and there's other ones where you'll get this kind of chaotic motion that doesn't, very, very sensitive to initial conditions. So, not going into all of how this works, but there's a built-in viewer in Clerk which is able to show off, use Vega or Vega Lite to go ahead and show charts. So we've got a closure data structure that represents a data set, and then more closure data that's able to tune the view of this particular inspector. So I've got here this kind of, I think really nice chart that in this case is plotting the positions of the pendulum bobs over time. Here we've got, this is the energy in the system. So there's sort of error that accumulates in the simulation. Here's the second angle over time. Here's the first one, and you can, well, look at that. You can scrub back and forth in the browser. Here's the chaotic initial conditions. Things look kind of more beautiful, but a little wacky. And you can see the energy is a little more jolty, but every once in a while, this thing goes off the top and cycles around as the pendulum, one whips the other one around. But so Clerk as a system is a visual REPL with an out-of-the-box toolkit that is useful for data science and many of the sort of default applications you'd want something like a notebook for. But it also has this ability to take a computer algebra system that has nothing to do with Clerk and install as a library all these other viewers for it that let you do things like physics simulations and Mathematica-style function viewing. And that's the hope here, is that this can be kind of a, Mathematica's great, it's closed source, can't really share anything. What if it were actually built out of open source components that were rateable and explainable?
Sam, actually, sorry to interrupt. There's a question here from the audience online. So they ask, can custom viewers be applied on a per expression basis as opposed to globally? And they name an example, which is render the tech version of a particular formula in Gothic script.
Yeah. Well, I can't do it live, but yeah, absolutely. If we look at this initial demo, when these forms on the left, this kind of Clerk tech, in this case, as you are noting, I did override the global viewer, and that's just like a convenience thing if you just want things to look nice. But you, on a per expression basis, where was it? Yeah, this Clerk with viewer is the answer to that. So you can say, look, just wrap this form up in a particular viewer and ignore the rest of the stuff. Just ignore everything else that's going on and override. Absolutely possible. I think that's all I wanted to show. So I've got this sort of interesting grab bag of stuff. It's not quite clear how it all hangs together, but maybe interesting, maybe exciting. Happy to take any more questions. Otherwise, we can.
More questions? Complaints?
Oh, complaint?
No, it's a question. In the pendulum example,
Yeah.
can you execute it over time and see it moving? Or it's just a plotting of the...
Yes, you can. The answer is the demo I showed yesterday where you had the bead kind of going around. I just didn't stick it in the pendulum notebook for now because it would have been, it's too intense. But yeah, absolutely. So that's a great thing is you can imagine the show-off suite of show me the equations of motion, show me a run for this many seconds from these initial conditions, and then also show me the, just play it in real time. And then change the initial conditions and the animation will restart much, much faster. The charts will fill in and you can see a bead kind of tracking real time as you go. So yeah, that's the idea, is that each of these things is like a tool in the workshop. And I want to see it live. Well, what does it mean that it's sort of all over the place? Okay, I see it now. I get what it means. And now let me go back to doing sort of 500 simulations at a time, and then I'll pick this one and move up and down this ladder of abstraction. And then end up with a closure source file, which has recorded this set of explorations you did, and you can go rebuild it.
Just wanted to say that I like very much your reasoning about like people don't want to leave their editors that they've learned over the years, and it's very important to respect that. And what I'm going to suggest, I don't know if this is necessarily a good idea. I don't have any problems with having a browser besides my editor, which happens to be the same as yours. But there are ways in Emacs to display pictures or to do non-editable fragments. So have you thought about that? Do you think it could be a direction in the future? There's even a way to embed a browser within Emacs. You probably know that.
Yeah.
That said, I think these tools need to be practical and usable right now, and I think this is the best solution right now, to have a browser beside Emacs. We use that for web programming. It's a very, very common way of working, so I think this is great. I think took the best route.
So it's a great question. I mean, pragmatically, Clerk has made this pragmatic choice of, okay, well, what do we all have available? We have a browser, and it's not, I should say, there's nothing Emacs specific. It's just watching files, so you can use any editor you want. That's great. Another thing that the ability to run in a web browser gives you is you can export this thing and have it run with somebody who has no environment set up. But that said, I do love living in Emacs. I think just to get any visual capabilities is, you shouldn't have to go start up this whole system. So absolutely, like when I work, in org mode gives you a lot of this amazing stuff. If you can have tech render and then go show it in line and have images in line. I haven't done the work yet of extending the closure REPL to do all that, but I think it suggests the right approach here of, I want to start with something lightweight. That's my REPL. I want to start to see a little more. Well, my REPL actually can do a lot more than I have it doing now. You can show math, you can show images. I can generate one of those Vega plots and show that in line in the REPL, no problem. Now I want to start preparing something to present to someone else. Okay, now I'm more of a typesetting mindset, so let's go to the browser and think about the fact that they're going to read it there. That's the idea.
So your idea is not to go WYSIWYG entirely?
No. The idea is that would be, like you could imagine a viewer in Clerk, which is a code mirror editor that will eventually emit like a closure file. But no, the idea is not to go WYSIWYG the whole way. It's to say, I'm gleefully staying in Emacs, but if you want other people to sort of consume this stuff and be able to play too, well, probably a WYSIWYG in the browser is a good idea. So someone can go, well, what if I change this? What if I change that? Yeah.
Can you open Emacs in the browser?
I can't. I'm sure someone here has probably figured this out. Yeah, that's it. Okay, so we'll re-implement Emacs in JavaScript.
So, yeah, give me the. To answer Yao, there's a package called maxima.l, happens there, I'm the maintainer, that you can basically render LaTeX in Emacs and have it similar way that you have it there, except I'm using a new plot instead of that. So aside from the pretty good and interesting moving parts, everything else can be done. For people who don't know, Emacs is also an algebraic system.
Great.
Sorry for the advertisement, but it's just to solve. So you want to stay in Emacs, and you don't care about other people not using Emacs, which is the right thing. You can can use that.
No, okay, that's great. I didn't know about that package, so that's really helpful.
So that's it. Yeah. Thank you.
More questions?
You said that if you move the slider in the browser, it gets sent back to your Emacs session and recalculated there. So it's not possible to export a large but still a static HTML file for somebody?
In that case, with that particular demo, yeah, that's fair. In that, the recomputation loop just wouldn't happen. I guess you're right. I think in that example, actually the browser is getting its recomputation locally. And then what will change is the re-rendering would be if I move the slider and it goes back to the atom and anything else depends on that atom value, then those statements would re-render. Does that make sense? Let's say I have, well, let's just do it. So let's say I show this, And then I'll say, you know, I want to plus the sign of with res box state with, I don't know, x. So let's see. Oh, couldn't resolve. Did I not import that? Okay, we'll just do as e for now. And then e/sign. Okay. So we've got here this example from before. We've got this like slider thing. If I go ahead and change opacity here, no, what did I do? Width res? Yeah. So if I change the width, let's see. I may be wrong. This may be you've pushed me into a demo that's broken. Okay, well, what this should do, what I thought was happening, was as you change this, the state here is also changing. And maybe if I do this, it'll work. So if I change this, the state should change. But then what should happen is this output should change as well, because it gets triggered by the atomic state shifting as well. And I think that cycle would break if you go and export this thing into the browser, this sort of pinging back and forth.
So dependencies between multiple operations break, but individual applications can be changed.
Yeah, that's right. That's right.
More questions? We have questions online? No. Okay, Sam, thanks again for the presentation.